Right, so the next speaker is Professor Gerd Rocha from the Federal University of Paraíba in Brazil. And he's going to be talking about various hardware acceleration activities that have been integrated into MOPAC in recent years.
Do you like? Do you see my screen?
I can see the screen.
Okay.
Yep. Okay. You're in presenter mode. You're good.
Okay. Thank you very much, Jonathan, for inviting me to present this lecture for you. I'm Gerd Rocha. I'm from Brazil, and I am professor at, sorry, my pointer here. I'm professor at Department of Chemistry at Federal University of Paraíba, Brazil. And I talk about how we accelerate MOPAC for high-performance computers with GPUs and parallel CPUs, okay? The first thing is the current challenge in quantum chemistry. I think many computational chemistry has recognized that the full quantum chemical treatment of larger molecular systems is a big problem to solve in this area. These systems including biomolecules, some materials, polymers, metal surfaces, and this topic become more hot. It's a hot topic after a Nobel Prize in chemistry in 2013 that won by these three researchers when they introduced many time ago methods, hybrid methods like QMM to model complex molecular systems. And now some researcher has identified some strategies to solve this type of problem, including the proposition of new theories, this including new parameterization and new methods like DFTB or parameterization like machine learning, coupled with machine learning, as the last speaker talked here. And other point is accelerate QM codes using fast and parallel high performance computers. And other strategy is to coding or programming new linear scaling algorithms to avoid some bottlenecks in the SCF algorithms. In this talk, in this presentation, I talk about these two points here. I think it's in 2007, NVIDIA proposed a new hardware to the user is able to program some kind of processors. And NVIDIA introduced general proposing graphic processing units, the GPUs. Automatically, the computational chemists see the possibilities to reprogram your traditional codes, focus on the CPU only, to explore this new hardware for doing some calculations, and you can see papers including reprogramming molecular dynamics codes and ab initio quantum chemistry codes, and so on and so on. Now we think about for semi-empirical QM codes, there's a traditional code, is MOPAC, and we already lots of experience to do some calculation with MOPAC, and we decided to accelerate MOPAC with GPU computers. And so our object was to accelerate semi-empirical calculations in MOPAC by using graphic processing units. This is the print of old website of MOPAC, and after our results, I will show the new website of MOPAC, including our link for our group, research group. And we started this work doing profiling with the MOPAC code and discovering where the bottlenecks, okay? And the main bottlenecks are in the SCF protocol, yes, and the operation that costs a great part of the time execution is diagonalization, full diagonalization, and some matrix multiplications. And we decide to change the normal execution of MOPAC from CPU to GPU using the available GPU libraries on that time, okay? And we use Cubeless, GEM, Cubeless subroutine to do this type of operation, linear algebra operation, and this a new code to rotate two vectors in this type of operation. And in some interactions of the pseudo diagonalization method, you have to do a full diagonalization, and we use the Magma library and Intel MKL. Okay, with this modification on the SCF code in the MOPAC, we did some benchmarks to know the impact of our changes, and we chose some systems, molecular systems, middle-sized systems like simulation boxes and proteins. Here is the speedups for water cluster, and our results showed we have 35 times faster with the simple modification in the MOPAC code. For another molecular systems, this is a methanol simulation box. We got 54 times faster for 1 SCF, complete 1 SCF calculation, okay? And we tested for fullerenes and proteins, small proteins, okay? And we continuing our modifications on the MOPAC code, changing other parts of the MOPAC where we found linear algebra operations. We are able to change to use the libraries for GPUs, okay? And for geometry optimization, we got a speed up of 29 times faster and 13 times faster. This is for something like fullerene, and this is linear protein, okay? And another location where you have impact for this time of calculation is the vibrational frequencies, because you need to mount a Hessian matrix, and you have to diagonalize this type of matrix. And we got speed ups of 9 times faster for this small protein, and for a larger protein we have larger speed up. The interesting point is the larger is the molecule, the higher is the speed up. It's very interesting point. Obviously, we reach a limitation by the memory of GPUs. We have a situation with this type of condition is not true, okay? And now I present the new MOPAC at the time, obviously, because MOPAC now is open source. Jonathan has do a lot of work to migrate to another portal, okay? But we have our results. You can follow our website showing with our implementations, okay? And in this picture of the portal of NVIDIA, and you can verify this tag of MOPAC 2013. I don't need. I don't know if this MOPAC 2013 exists, but it's very funny. But in this portal of NVIDIA, you can check the acceleration of MOPAC by using GPUs from our results. Another topic I can bring here to discuss is the other improvement of MOPAC. Is a local version of MOPAC, our local version. A proposition of new algorithm to do linear scaling calculation, okay? And we apply this method to compute a large molecular system, including this big drop of water and this big wire of protein, okay? And the heart of this method is the multiplication of two density matrix to form the square density matrix. This is a property of matrix that we consider by the projection matrix, okay? And this type of method is named as purification of density matrix method. And the heart of method is to avoid the use of C matrix or the molecular orbital coefficient matrix, because it is not a sparse matrix. And this method, PDM method, it is based on the exploring sparse matrix formed when you have a big molecule, because the density matrix is formed by electron-electron interactions, essentially. And when you have one electron in one orbital in this location of the molecule, and the other electron far away on another orbital far away from this, the element of the matrix is almost zero. And why do you have to calculate zero elements? It's not a good idea. But if you choose to follow the way of do Hartree-Fock methods using coefficient matrix, molecular orbital coefficient matrix, you not take advantage of this type of situation. And PDM is a proposition to avoid the use of non-sparse matrix, and you avoid also to diagonalization matrix, for example, Fock matrix. And PDM is a very elaborated method, but essentially you need to expand this type of
Rocha,
function.
could you wrap up in a few minutes? You're starting to run over time. Are you almost done?
5 minutes?
Well, you're very close to out of time. Could you wrap up in like one or 2 minutes?
2 minutes, okay. And you need to in the heart of the methods, you need to do something like this, a multiplication of matrix and calculation of the trace of matrix. And we program this type of multiplication using the native format of allocation in the memory of Mozyme. This like this is the symmetrical variable block row sparse format, and we propose a new form to do this type of multiplication. And this is the results. We prove this method is linear, is a log scale. The coefficient is almost linear, and that is the speedup related to on the CPU and GPU. This is the speedup for the CPU, and this is speedup for GPU, for polypeptides and also for water boxes. a calculation, the larger calculation we had, considering 42,000 basis sets in one GPU. Propaganda of my lab. This is we are do theoretical and computational projects, create new codes, parameterization semi-empirical methods, and proposition of new linear scaling methods. And we apply this type of development in to study many molecular systems. And finally, I will show you where I live. Here is the map of the Brazil. My state is here, Paraíba. João Pessoa is a beautiful place to study, to work, and to live. It has a lot of culture. It is also known as the city where the sun rises first, because it is the easternmost city in the Americas. This is the sunrise at Jacaré Beach when this saxophonist plays Bolero de Ravel all time. And João Pessoa is considered one of the greenest cities in the world. And this is the view of beautiful place. It's a bank of sand. We sit here eating dry fish and in the middle of the ocean. Okay. And the more important thing is the temperature of the seawater is around 27 Celsius degree. Is a great temperature for enjoy the beach and the summer. Okay, I need to thanks to the founding agencies of Brazil, and this is the group. Okay, thank you very much for my presentation.
All right, we have time for maybe one quick question before we move on. Does anyone have questions? I guess I should note, so I did mention in my talk, so all of your contributions associated with multi-threading and using Intel MKL and BLAS and LAPAC, those are all well preserved in the open source version right now. But the GPU work is presently disabled, and that's something that it's been a challenge to migrate that to the CMake build system. And as you showed in some of your benchmarks too, like really given the state of the multi-threaded CPUs and the GPUs, at least back when you were looking at those benchmarks, it was often the case that the multi-threaded CPU would win out in the end. And so when people were looking for the way to run MOPAC the fastest, usually it was just multi-threaded CPU that was the best option for most people.
Yes,
So
I agree.
The pressure to the usefulness of reactivating the GPU, it just hasn't quite been the highest priority. Right now.
Yes. I think I would like to do this again, and I have to this opportunity to revive this type of work.
Yeah. I mean, definitely the GPUs aren't going away, so there's going to be opportunity in the future to do something with them again.
Okay, thank you very much.
Yeah. So now let's move on to the next speaker.